Well, here we are. Grab a notebook, grab your pen or pencil, whatever you want to write with, and bring your focus to this session. This is math from the void. Math coming at you out of nowhere. Today we have a problem from the 1994 AP Calculus AB exam. And here we have a curve that is defined by a relation. This is not a function. So, if we do any derivative stuff here, which we will, we're going to have to do implicit differentiation. And we're going to get cracking with this, starting with part A, write an expression for the slope, which is dy dx of the curve. Now, like I said, this is going to require us to do implicit differentiation, so this should be a very easy step. You see that we have a product here, x times y. So just be aware of that. It's pretty common to see that in implicit differentiation problem. So if we take a derivative of both sides of this, we end up with 2x plus, remember how to do the product rule, and also remember that anytime we take a derivative of what I like to call y stuff, any y stuff is going to just give us dy dx. So the derivative of x is just 1, and leaving the y the same. Plus, now we're going to leave the x the same. We're going to take the derivative of the y, and that is our desired dy dx. Now, we still have some more stuff on the left side, so that's plus 2y, just from the power rule. But like I said, anytime we take derivative of y stuff, we're going to have dy dx. And on the right side, we just have 0. So in order to find the slope of the curve, dy dx, we have to isolate dy dx. So we're going to move anything that does not have dy dx to the right side. That means we're going to subtract 2x and we're going to subtract y, negative 2x minus y. And then we're also going to factor out dy dx. Let's move this in a different spot slightly. Now from the left side, we're going to factor out dy dx. And what would we be left with? Well, we would be left with x and plus 2y, right? If we factor the dy dx out, we're left with x. If we factor the dy dx out, we're left with plus 2y. So we have to divide those things out. And now this is an expression for the slope. So this is going to give us the slope. As long as you give me an x and a y value, I can find you the slope. Okay? Determine whether the lines tangent to the curve at the x-intercepts are parallel. I want to determine if these are parallel, which means their slopes are the same. And we have to show the analysis that leads to the conclusion. So first, let's focus on this x-intercepts. What do x-intercepts mean? X-intercepts mean y is equal to 0. Okay, well, that's pretty easy to start off with, because if y is equal to 0, then based on the original equation, the points that we have on the curve are x squared plus 0 equals 27. And therefore, x equals the square root of 27. X squared equals 27. Therefore, x equals plus or minus the square root of 27. So that's plus or minus 3 square root of 3. Okay, and we know that the y values are 0 there. So let's see if the slopes are indeed parallel. If the tangent line has the slope of the curve at that point. So we can just look at the slope. Let's plug it in. So dy dx for the positive square root is going to be negative 2 times 3 square root of 3 over 3 square root of 3. That's because the y value is 0 at these x-intercepts. So the derivative here really just depends on the x. And so this is just negative 2. Now let's check dy dx for the negative square root 3 of square root 3. So this would be negative 2 times negative 3 square root 3. But then it will also be over negative 3 square root 3. So again, we just get negative 2. So indeed, they are parallel. Parallel tangent lines at the x-intercepts. Okay, not too bad at all. Now we have to find the points on the curve where the tangent line the lines tangent to the curve are vertical. What does this mean? This means that dy dx is undefined, but more precisely, it means dy dx is like approaching infinity. So that means that the denominator of the dy dx expression is equal to 0. So we have negative 2x minus y over x plus 2y. What we're saying here is that this bottom portion is equal to 0. And this is common of some implicit differentiation type problems. We're going to get a connection between x and y. We're not going to solve for one of them without having the other in its terms. So let's just say that x equals negative 2y. As long as x equals negative 2y, then x plus 2y equals 0, then the slope will have a 0 in the denominator, which means we have a vertical tangent that we're looking for. So how do we use this? How do we use this connection? We must plug this in the original curve equation. So we just basically make a substitution. That's all we're really doing here. So we're going to have, and you can do this with the x or you can do this with the y. It's totally up to you. I just chose to replace the x with negative 2y squared plus x times y, which is negative 2y times y, plus y squared equals 27. So by doing this substitution, I'm going to find y value, or maybe y values, and then I can use those y values to simply plug back in here and find my x values. Okay, so let's see what this turns into. This turns into 4y squared minus 2y squared plus 1y squared. Well, that's easy to work with, isn't it? That's just going to give us 3y squared equals 27. Therefore, that's going to give us y squared equals 9. And that means that y equals 3 is a solution and y equals negative 3 is a solution. Now, these points have x values that go with them. So we need to plug into this substitution equation that x equals negative 2y. So in this case, x equals negative 2 times 3, which is negative 6. And in this case, x equals negative 2 times negative 3, which means x equals 6. So the points on the curve where this tangent line is vertical, that's going to be at negative 6 comma 3 and positive 6 comma negative 3 have vertical tangent lines. It's always good to like write this kind of thing out. If you just write the points and say I'm done, you can trust the graders of the AP exam to be pretty smart and they're going to follow along, but they're not necessarily always trying to give you the points and always trying to give you the benefit of the doubt, so don't really count on that. Make sure that you have a nice brief summary of the solution and your logic. So these points have vertical tangent lines, and I think that's the best way to say it. Okay, so this question was a pretty light curve. We didn't have to do too much crazy stuff with the implicit differentiation. You guys should start to recognize structures like this. Pretty simple curves. And we don't have to talk about what the curve actually looks like, but if you're interested, I encourage you to graph this and play around with different values and see how that affects what the curve is. You might be interested in what kind of shape that is. And then you could also look at these points specifically. Negative 6 comma 3 and 6 comma negative 3, you could check that they go vertical at those points. You could even look at the points that we got from part B with the x-intercepts and make sure that those are actually x-intercepts, right? 3 root 3 comma 0, negative 3 root 3 comma 0. So those are like extracurricular things. You wouldn't be worried about that when you're taking the exam, but since you're still at this point of preparing for the exam, I think it's helpful for you to learn about some of these structures, and maybe you can improve your performance if you get a question similar to this on the exam. All right, that's enough rambling from me. Hope you had a good time. Hope you remembered the rule for differentiating when we have a relation and you have to do implicit differentiation. Other than that, we're just applying tangent line analysis, basic derivative analysis here. And that'll do it for me in the void today. I will catch you next time.